Today I will be discussing Lab 5, which was the Create Your Own Adventure Lab. For this lab, I chose to model the motion of a basketball shot. The objective of my lab was to find the kinetic energy lost during a basketball shot due to drag and other forces that are unseen and that are acting on the ball. The results of my experiment were that the model did have a higher final kinetic energy, and there was a difference of about 0.75 joules between the model and the experimental data. For this lab, I will be creating a computational model of a basketball shot that I took and captured on video, and then modeled in Tracker. This experiment will use Newton's second law to determine the positions and the velocities of the ball at each time step. It will also use the kinetic energy formula, where kinetic energy is equal to 1/2 the mass times the velocity squared. This will be used to determine the final kinetic energies of the experimental data and the computational model, which we will compare to see how much energy was lost. This is a video of me shooting a basketball from the three-point line. I chose to start my analysis at the instant the ball left my hands, which is where you can see the axes at right now. If I play the video, you can see that the ball moves in an arc and lands in the net. Looking at the data we extract from Tracker, we can calculate an initial velocity using the first two data points, and then we can graph the whole data to compare it to our model later. First, I have to set the initial conditions that I will use to create the computational model. The ball's mass is set at 0.62 kilograms. The ball's initial position is at 0, 0, 0, or the origin, and the ball's initial velocity was found from the first two data points in Tracker. And the time step is 0.033, which is the time step for my video recorder. Next, we will look at the calculation loop of my code, which is where the positions are actually found. I set the force of gravity equal to the ball's mass times the gravitational constant times the unit vector in the j direction, which is vertical, and set this equal to F net because we are assuming that is the only force acting on the object. Then we find the ball's velocity with Newton's second law, and then we find the ball's new position and advance the clock. If I run my code, we can see that the ball moves in an arc to the left, which is the negative x direction. Looking at the graph, the blue line is the y coordinate of the position, and the red line is the x coordinate of the position. The slope of the x coordinate is not changing, which means that the velocity in the x direction is constant. This seems to be true because the force of gravity only affects the y direction. After receiving the model data from Python, I created a graph which contains both the model data and the experimental data. Looking at the graph, specifically the experimental data, we can see that the ball loses some of its velocity as it flies through the air. This is due to a drag on the object, which we did not account for in the model. Using the final two data points in each set of data, I was able to determine the velocity with delta r over delta t. With these two velocities, I calculated the kinetic energy of the experimental data and the model data. The model data, as you can see, was approximately 0.75 joules higher than the experimental data, which I went ahead and said that this was due to the drag on the object. Because the motion of an object through air is always affected by some force due to drag in normal conditions on the Earth, I went ahead and said that the difference in kinetic energy which was found to be about 0.75 joules, was due to this force due to drag on the object.